Hello, everyone. Good afternoon. Um, Today, I'm going to talk about the new Ceph Messenger protocol that was developed for Nautilus. My name is Ricardo Diaz, and I'm a senior software engineer at SUSE. So today, we're going to talk about. I will start with more or less explaining what's the Ceph Messenger component, why we required to develop a new wire protocol, what was the problems with the previous existing one, well, still existing one. I will then talk a bit more in detail about the new protocol, which we called Messenger v2, and I will show you some of the details of the protocol. I will also talk a bit about the new feature on that protocol, which is On-Wire-Encryption. And I will finish with some administration tasks on how to enable the protocol, how to disable, what things we can configure in it, and also some details about the upgrade from Mimic or should be from Luminous and later versions. All right, so what's Ceph Messenger? It's a wire protocol, but it's also the corresponding software implementation. So when we refer to Ceph Messenger, we are talking about both the component and also the wire protocol. Usually, it's invisible to end users, and if it's not, it's because something is broken. Right? Some problem exists in your cluster. And also, one thing important is that the Ceph distributed algorithms, the OS, the PG peering, all those, the Mons, quorums, they are built on top of Ceph Messenger. So the Ceph Messenger is just the communication library. It doesn't know anything about what's going on above. So basically, the Ceph Messenger component, it's everywhere, both on the server daemons, like Mons, OSDs, managers, MDSs, and also on the client libraries, like in librd, librgw, the CephFS client. All of those have this small component that allows them to talk to each other, basically, through the network. So, yeah, Messenger is a small communication library, okay, that all Ceph components uses to talk with each other. This small library can be used both as a server and a client. Okay? So because you know that OSDs both and other components act both as servers and clients. They are listening for requests. They are sending requests to each other. And yeah, and RBD and RGLab are just clients. The Ceph Messenger also abstracts the technology used for the physical communications. So it works above the network layer. So and abstracts. It can be used in above POSIX sockets or RDMA or DPDK. It ensures a reliable delivery of messages within exactly one semantics. Sorry, and it also takes care of. It also handles some of the connection failures. So when some connection fails temporarily, Ceph Messenger will try to handle it and try to reconnect to the other end, and so that the algorithms that are built on top of it don't need to handle those cases, basically. So why did we need to design a new protocol? Why didn't the existing one was not enough? So Messenger v1, or just Messenger, was the first wire protocol in Ceph, so it was there since the beginning. And one of the problems was that it didn't allow us to extend the protocol. So if we required to make changes to the protocol in a very early stage, it wasn't supported. And the only way to change the protocol would be to introduce breaking changes. So there was no possible to extend the protocol and still be compatible with previous versions of Ceph. It also didn't support, it didn't guarantee data authenticity, neither supported data encryption, which is a security requirement. It was also very limited on the different authentication protocols that we could use. It was tightly coupled to the CephX authentication scheme that we use in Ceph. And also the protocol design was, it didn't have a very structured messages in the control, the protocol control messages were not very structured, and it was just, it needed some refactoring. And so these requirements or these limitations led to the necessity of creating a new protocol. And this was what led to the V2. So the Messenger V2 is basically a complete redesign and implementation of the protocol. It was designed since from the beginning to be an extensive protocol. So it's a protocol that we can change the behavior of the protocol almost from the beginning when the peers start to connect. So allows us to extend it without causing breaking changes with previous versions. It was also made in a way that allowed to plug in different authentication schemes, okay? Not only CephX, but others. And was also done with to support on-wire-encryption. So in Ceph Nautilus, the V2 protocol is available on port 3300 for Ceph Mons. And we didn't remove the V1, otherwise we wouldn't be able to connect to clients from previous versions could not connect to Nautilus. So we are basically, Ceph Mons are now listening on two ports. One is the V1 port, the 6789, if I'm not mistaken, and the new V2 port, which is 330. Also, another important remark is that only user space libraries support V2 currently, so librd, librgw. But kernel modules like KRBD or the CephFS kernel module still talk the V1 protocol. So, okay, so I'm going to show you briefly how the protocol works. For that, I will always have a client and a server. And the protocol can be split in four phases. So the first phase is called the banner exchange, then the authentication, then it proceeds to the session, handshake, and in the end, the message exchange. The first three phases are basically the initial negotiation between peers, and then as soon as that initial negotiation finishes, it will become both peers become either client or server and can exchange message between each other. So for all the control messages of the protocol, they have a fixed structure, which you call the message frame. Okay? And the message frame has three parts. It has the preamble, the payload, and the epilogue. This is the message frame for the no encryption mode of the algorithm. Okay, and so the preamble it has many fields, but so the first one is actually the type of frame. Okay, so each control message has a type, and that's specified on the first 8 bits of the preamble, and then we have the number of segments of data. Okay, and this will tell us basically how much segments have the payload data. Okay, for the control message or the data message. Then we have, for each segment, we have the size of the segment, so we know how to read the rest of the payload of the frame. And in the end, it has a CRC field so we can check integrity to ensure that the integrity of the preamble. So after these 32 bytes, we have the payload, which is basically the sum of the 4 segments sizes. Usually, the control messages for the negotiation only use 1 segment, and then the data messages use the remaining segments. And after the payload comes the epilogue, which has some flags, and it also has the segment CRCs to check the integrity of each segment. Okay. So every time we send a message to the other side, we basically pack the payload inside this frame with this structure. So banner exchange. The first thing that happens when the network connection gets established between both the client and the server. For instance, if we are using POSIX sockets, as soon as the TCP connection is established, both the client and the server will send the banner message. Okay? The banner message is the only exception that is not packaged inside the frame. Okay? It's a message that has a simple string, readable string called Ceph v2. And then afterwards, we tell which is the banner length, so how many bytes it takes our banner. And currently, we are just sending 2-bit masks. What are the supported features of this peer, and what are the required features? And by using these bit masks is the way we can actually influence the behavior of the rest of the protocol. Depending on the values of these bit masks, we decide whether if we are in a different version, or which features does the other peer support, and so on and so forth. Okay, so after exchanging the supported features and required features with each other, and they send this message in parallel. When both they receive the banner from each other, they send an hello message, an hello frame. This hello frame serves to indicate what kind of entity I am. So if I'm a mon, an OSD, a client, okay, and also my address. Okay, what is my address? Okay, so after this initial exchange of the banner and the entity, we start with the authentication. So the first thing, the client sends an auth request to the server. Okay? And in this auth request, it specifies what is the authentication method that he wants to use. Currently, we only support like no authentication SIM, so I'm doing an authenticator at all, right? Or using Cephx, which is what's implemented, and maybe in the future using a Kerberos authentication scheme. So after the authentication method, we specify what are the preferred modes of the connection. And currently, we only have two, CRC or secure. So CRC is our traffic is unencrypted, okay, and not signed. And we just make integrity checks using CRC codes. Okay? The secure mode, on the other hand, will give you the on-wire-encryption functionality. So all traffic will be encrypted and signed. So then there's also some payload bytes that are dependent on the authentication method that you choose. So now the server, when receives this, can decide if it supports the authentication method or not, and if it doesn't, and also if it supports the mode, right? And it can reply to the client, say, I don't support this, please, I only support these methods and these modes. So then the client needs to decide what to do, right? And it can perform another auth requests. And now, if the server is okay with what the client is requesting, it replies, okay, with a message called auth reply more, okay. And the client can then send another auth request more, okay. And we can go back and forth as many rounds as we want. And this allows us to plug in here different authentication schemes that have more rounds or less. So this will finish when the server responds to the client with an auth done message. Okay? And in this auth done message, he basically says, OK, here's the global ID and my global ID. Here's the connection mode. So if we are going to use CRC or secure, and also the remaining auth done bytes. Yeah. So when we are done, when server gets done, there are two more messages that are sent to each other. Both the client and the server, while they were exchanging these authentication messages, they were calculating digests of all traffic. And in the end, they sent to each other that digest to guarantee that there was no interference on those. There are no reply attacks and other kinds of attacks to make sure that nothing happens between the authentication negotiation. So at this point, when both receive the auth signature frame and they check that everything is OK, they they pass to the session handshake. So the first thing is the client once again initiates the session establishment. And when it's a new session, so the peer it's connecting for the first time, well, sometimes it's not the first time, but when the client doesn't know, it's not aware of any previous session. For instance, if your daemon has crashed and it's restarted, it will send a client identification frame to the server, which has a lot of information like what are my addresses, who is the address of whom I think I'm contacting, my global ID, what are the Ceph supported features and what are the required, and also, very important, the client cookie, which will be used which will identify this session, at least on the client side, and will be very useful for when reconnecting to sessions. The server, on the other hand, when receives the client identification, if everything is OK for him, he will reply to the client with his server identification and also with all this information, also about the features, and also important, the server cookie, okay, which identifies the session from the server side. So when there is some connection failure, so the peers are already sending messages to each other, and there is a connection failure, the peers are able to reconnect to a previous session, okay? And this starts also with the client. So basically, when there's a reconnection, it performs the authentication, and then instead of sending a client event frame, it sends a reconnect frame. And in this reconnect, he sends the client cookie, okay, and the server cookie. Okay. And it also sends some sequence numbers, so we know if it's not a duplicate reconnect and other stuff. But it also sends the message sequence number, which is like, what was the last message that I saw from you? Okay. The server will look at this message, will check if the client cookie matches with something that you know in the past. We'll also check if the server cookie matches for that session. And if everything is OK, it will send a very simple message saying, OK, I accept your reconnect. And this is the last message sequence number that I know that you've sent to me. Okay. So after this step, everything is OK. So both for the new session and for the reconnect, they are prepared to start sending message to each other. Okay. So at this point, both peers can send messages received, and they will also piggyback acknowledgement to tell the other peer, I already received the message with that sequence number. And yeah, this is the traditional way of guaranteeing some stateful, the stateful session. So each message frame, as I said before, they use the four segments. Okay. Right. So this was so for getting the on-wire encryption. So if during the authentication phase, if they agreed on using the secured mode, right? It means that now all the traffic starting from the session negotiation is supposed to be encrypted. Okay. And what we do is we encrypt the whole frame. Okay? And the frame, it's very similar to the unencrypted frame. The only difference is the epilogue. The epilogue has different fields. Currently, we are using a stream cipher called AES 128 GCM. Okay? It provides authenticated encryption and decryption, so it guarantees confidentiality and authenticity. So the preamble in an encrypted frame doesn't change. The payload it also doesn't change, and only the epilogue. The epilogue basically has the same flags that he had in the unencrypted form. And then he has some padding to fill up the first 16 bytes, and afterwards it has n bytes of data that depends on the encryption algorithm. Okay. So some administration steps. So as I said in the beginning of the presentation, we implemented the new protocol, but we still need to have the v1 protocol, because both the kernel drivers still, they only talk v1, right? And if you have an old user space client connecting to the cluster, he will also only be able to talk the V1 protocol. So which means that we had to support to have the two protocols be working out at the same time. So the mons need to be listening at both the V1 and V2. For that, we had to develop this notion of the address vector, okay? And now daemons can be identified instead of just a single address. They can be identified by a set of addresses. Okay? And this allows us to specify what is the what is the port that the V1 protocol is listening to, and what is the port where V2 is listening. And I have here an example of the mon host configuration option. Now we can specify for each mon inside brackets a list of of addresses, and we have to prefix the IP address with the type of the protocol. So if it's V1 or V2, and then specify the port. Okay. Of course, we also allow you. We still allow you to specify as you were used to by just specify a list of addresses for each mon, and these are equivalent. So if you just specify the IP address, we will assume that you will use the default ports. So the 6, 7, 8, 9, 10 for this is switch. There's a typo here. So we will basically, if you just specify only the address, we will be listening the V2 on the 3300 and V1 on 6, 7, 8, 9. Okay. So with the V2, it also come new configuration options. So now we have MS bind messenger 1 and MS bind messenger 2. This specifies if the daemon should bind to the V1 or V2 protocol. And we can set to control if we want the CRC mode or the secure mode. We have these config options. I have here the descriptions. The MS-mon cluster mode specifies the modes for the connections between monitors. The mon service mode specifies the modes when services connect to mons. Mon client is when clients. It's the mode for the clients that try to connect to monitors. And then we also have the cluster mode, which is the mode for the intra-cluster connections, the service mode, and also the client mode. Okay. So all these config options have default values. You should check them out. What are the default values for Nautilus? And you can change these options to just choose CRC, or for some cases CRC and others secure. Okay. So Messenger 2 is enabled by default. So if you deploy a Nautilus cluster, the mons will immediately starting to listen on V2 and other daemons as well. If you want to disable the Messenger V2, you just add to your Ceph conf file or to the config store the option MS bind messenger 2 equal to false, and then reboot the daemons. Okay, and daemons will stop listening on the V2 protocol. And if you want to re-enable, just undo the same things. So upgrade. So actually, upgrades from Luminous or later, which include Mimic, you will probably see you have a Luminous cluster. You do the upgrade for Nautilus. You will probably see this message saying that the monitors don't have the Messenger 2 enabled. Okay, so this basically means that after an upgrade, if we want to use the Messenger 2 protocol, we need to explicitly tell the cluster, please start using the Messenger 2. And we can do that with a mon command called ceph mon enable Messenger 2. Okay? But there's a catch here. We can only use this command if your cluster is using the default ports for the V1 protocol. So if your mons, their configuration, they are listening on the 6789 port. Okay? If your mons have a custom port for some reason, you cannot run this command. To fix that, you will actually need to change the mon map manually and set the port for the V2. Because probably if you're not using the default port for V1, probably you want to also custom the V2 protocol for firewall reasons or something. And since we cannot guess which port the user wants to use, the user needs to manually adapt the mon map. And yeah, this is the presentation. Don't have anything else. So any questions or doubts? Yeah.
You had mentioned there's CRC.
Yep.
Does it using just CRC32, or are you doing some sort of like secure hash?
So the question is if in the integrity checks, if we are using simple CRC32 bits or if we are using authentication message codes like MAC message authentication codes or something. No, for the CRC we are using simple CRC32. Yeah. Where? Sorry.
Why not to reuse the same port for protocol version 2?
Oh, okay, so the question is why don't we reuse the same port for the V2 protocol? Because we still need the V1 in there. Well, you're telling us that we could decide whether we should go through the V1 path or the V2 path based on the first byte that we receive from the connection. I would have to think what are the implications of that. So I will not respond it here. I'm sure that the code would become much more complex to achieve that, and yeah. Yeah. You need to change firewall rules, add, yeah. Mm-hmm. Yeah. Right. Yeah, I understand. Yep. when using the encrypted mode. So the question is if there are performance impacts when using the encrypted mode. And yeah, so the encryption mode will, of course, will have an impact on performance. We don't have numbers yet, so yes, I'm sure there are. I just don't know how much is it. So we still haven't run the performance benchmarks. My very early experiments some time ago, and I was using a different encryption algorithm. I was already seeing a 20% of overhead, but we switched to a different encryption algorithm, and we still haven't any numbers.
You mentioned that authentication happens first and then encryption happens. Does this mean credentials are somehow...
So the question is, I told during the presentation that first happens the authentication and we only start encrypting messages afterwards. Well, the authentication control messages, they are secured. There's no credentials passing in plane because they're using currently to use a Ceph and they have these keys. They know, everyone knows keys of it. The mods know the client keys, and yeah. So the authentication payload, it's encrypted and follows. Yeah. No security issues that I'm aware of. Any more questions? Oh. Well, thank you very much for listening.